Hello and welcome to yet another calculus video of Cornerstones of Math. If you haven't seen my previous calculus video, please check the link on the top right corner. Today's problem is point A departs from the initial position, which is x equals 0, with initial velocity of 3 meters per second and moves in positive x direction with constant acceleration of 1 meter per second squared. Point B departs from the initial position 2 seconds after point A does and moves in positive x direction with constant velocity of k meters per second. What is the minimum value of k that 2 points meet? Okay, first, let t equal 0 be the moment when point A departs. This means that point B departs at t equals 2 seconds. Now we must find the positions of A and B as a function of time. First, point A. The velocity of point A, denoted by VA, can be obtained by VA0, the initial velocity of point A, plus the integration of acceleration of A over time from t equals 0 to an arbitrary time t. Here, the initial velocity is given as 3 meters per second, and we have a constant acceleration of 1 meter per second squared. So we have 3 plus integral 1 dt from 0 to t, which gives t plus 3. And the position of point A, denoted by xa, is given as the initial position of A plus the integration of velocity of A from t equals 0 to t. Here, the initial position is simply 0, as given in the problem. And using this VA we just obtained, we have 0 plus integral t plus 3 dt from 0 to t, which gives 1/2 t squared plus 3t. So this is the position of A as a function of time. Meanwhile, the position of point B at time t, denoted as xb, is much simpler because B is moving at a constant velocity of k meters per second. So its position is given as velocity k multiplied by time interval, which is t minus 2, because point B departs at t equals 2 seconds. So this is the position of B as a function of time. From here, we can find the minimum value of k with two different approaches. So let's start with the first one. First method. Using the fact that equation xa equals xb must have real roots in a certain interval. It's much easier to understand if you just keep watching the video. So in this method, we will extract the conditions for k by setting up the equation. When 2 points meet, xa equals xb, and therefore 1/2 t squared plus 3t equals k t minus 2. And if we multiply 2 on both sides, we have t squared plus 6t equals 2kt minus 4k. So we have t squared minus 2k minus 3t plus 4k equals 0. And the condition is that this quadratic equation must have real roots at the region where t is greater than 2. And to handle this condition, we will use the properties of a quadratic function. Here, let ft be the left-hand side of the given equation. Then f2 equals 4 minus 4k minus 3 plus 4k, which just gives 16, which is positive. Now, if we state the condition again, we want the quadratic equation ft equals 0 to have real roots when t is greater than 2. Therefore, the graph of the quadratic function ft must look like this. So f2 is positive, and the graph must meet the horizontal axis, the t-axis, when t is greater than 2. In order for the graph to look like this, we need two additional conditions. First, the axis of the quadratic function must be on the right of t equals 2. So from the quadratic function, the axis is t equals 2k minus 3 divided by 2. So it is just k minus 3. Therefore, k minus 3 must be greater than 2. So we have k greater than 5. So we have this range for k. Next, the quadratic equation ft equals 0 must have real roots, that is, the graph must meet t-axis in the first place. And this means that the discriminant of the quadratic equation must be non-negative. So from here, the discriminant is 4k minus 3 squared minus 4 times 4k, so 16k, which must be non-negative. So we have k minus 3 squared minus 4k is greater than or equal to 0. So we have k squared minus 10k plus 9 is greater than or equal to 0. So k minus 1 times k minus 9 is greater than or equal to 0. So we have k greater than or equal to 9 or k less than or equal to 1. So we have this range for k. Now if we find the common range between 1 and 2, we have k greater than or equal to 9. Therefore, the minimum value of k is 9. So that was the first method. So we have set up the quadratic equation using the position we have obtained, and we have utilized the condition that the given quadratic equation must have real roots in a specific domain. The condition which is handled using the properties of the graph of a quadratic function. Now let me introduce the second approach. Second method, using the fact that graphs of xa and xb must meet. In the second method, we are going to extract conditions from graphs right from the start. We can plot positions xa and xb as a function of time, which gives these xt plots. Notice that the graph of xa is a parabola that passes the origin, and we can easily draw its graph using the basic knowledge of a quadratic function. For the graph of xb, notice that xb is a linear function of time, so the graph must be a straight line with slope k. Here, you can also notice that the graph always passes the point 2, 0, regardless of the value of k. Therefore, possible graphs of xb are lines that passes the point 2, 0, as shown in this figure. Here, we want that two graphs xa and xb meet each other. Therefore, k, the slope of the line, is minimum when the graph of xb becomes the tangent line to the graph of xa, like this figure. So let us find the minimum value of k using this tangent condition. Let the point of tangency have t-coordinate of alpha. Then, using the obtained position xa, the x-coordinate must be 1/2 alpha squared plus 3 alpha. So this point is alpha, 1/2 alpha squared plus 3 alpha. First, the slope condition, aka derivative condition. At t equals alpha, the derivative of xa with respect to time, which is actually the velocity va, and also the slope of the parabola, must have the value of k, the slope of the line. So the derivative is given like this. So we have alpha plus 3 equals k. Next, the values of two functions condition. That is, the two graphs xa and xb must have the same value at t equals alpha. So 1/2 alpha squared plus 3 alpha equals k times alpha minus 2. So we have two unknowns and two equations. Substitute equation 1 into k in equation 2, we have 1/2 alpha squared plus 3 alpha equals alpha plus 3 times alpha minus 2. So 1/2 alpha squared plus 3 alpha equals alpha squared plus alpha minus 6. And if we multiply 2 and rearrange, we obtain alpha squared minus 4 alpha minus 12 equals 0. So alpha plus 2 times alpha minus 6 equals 0. And since alpha must be positive, alpha must be 6. And from equation 1, we have k equals 9, which is the minimum value we seek. So that was the second method, where we extracted the conditions from the fact that two graphs must be tangent to each other. And that's all for today's video. Please hit the like and subscribe buttons, and as always, I will see you in another video.